As we begin to explore circles, the next topic we're going to touch on are tangent lines. And tangent lines aren't particular to circles, but in this case, because circles have the same radius all the way around, it causes some pretty interesting situations. So, a tangent line, something to understand is a tangent line is a line that touches the circle at exactly one point. So it doesn't cut through the circle, it touches it just barely at that one point. And because of that, it has to be perpendicular to the radius. If it wasn't, it would end up cutting through the circle and it wouldn't make that perfect 90-degree angle. It would also not be considered a tangent line if it went through more than one point. So, 90-degree angles create a lot of interesting situations. So the first thing we're going to study is Theorem 10.3, and I just labeled it the same as your geometry book. And that's if two tangent segments, so this is not a line, this is just from A to C, for instance, a line segment, if two tangent segments intersect the same point, so they go through the same point, then they must be congruent. And you can kind of see why that might be. As we create these two right triangles, they have to have the same radius. They have to go through that same point, so that means that the distance from the center to that point is going to be the same. And so we end up with a situation where we have basically two congruent triangles creating those two congruent segments. So let's see how this might be useful. All right, our first question is how can we determine if AB is tangent to the circle P? So if you are noticing, here's our notation for our circle, and it's based off of the center of the circle. So I'm calling it circle P because P is the label for the center. Well, I can tell if this is a tangent segment if it is perpendicular to the radius. So if AP is the radius, then AB has to be perpendicular to it. Well, you might be noticing that this forms a triangle. So if this happens to be a right triangle, then we can use that information to infer that this angle is a right angle, and therefore it would be tangent. Lots of different steps there in our kind of logic, but it all kind of goes together. So we're going to use what's called the corollary of the Pythagorean theorem. So normally when we have the Pythagorean theorem, we're missing a side. And in this case, we're given all three sides. So we have to figure out, is this a right triangle? So instead of using an x or something like that, we're going to plug in all of the values. And we have to make sure that C, or the hypotenuse, is the longest side. So this is where that comes in really handy. 17 is the biggest number, so it has to be the longest side. I do some math, and you'll notice I add this little question mark because I'm not saying that they're equal. I'm trying to figure out, are they equal? And at the very end, I get 289 on the left is equal to 289 on the right. Bada bing, bada boom, they're equal. That means that they follow the Pythagorean theorem, which means that it is a right triangle. And if it's a right triangle, you have a right angle. And if you have a right angle in this particular case where we need it to be, that means that AB is, in fact, tangent. Another thing you might be asked to do is remember that the two segments are congruent, which means that they are equal. Now, if two things are equal, we can set them equal to each other in an equation like this. If you're asked to solve an equation with variables on both sides, I highly recommend subtracting the lesser from the greater. The reason we do this is that we end up more often than not with a positive coefficient. So here we have a coefficient of 1. I didn't write it in because, well, you don't really have to. 1x is the same as x. But if I had done it the other way around, I would have gotten a perfectly valid answer. I just would have had to deal with some negative numbers in the meantime. So, two ways to do the same thing. This is just an easier way if you don't like dealing with negatives. I always focus on which one has the smaller coefficient, and I take that one away or add it if it was negative. Our last type of problem today deals with the fact that we can use information about this being a right triangle to find information about the figure. So in this case, we're looking for x, and x is just the distance from the circle to this point outside of the circle on the tangent line segment. We have essentially a right triangle, but they didn't draw in the right angle. So a lot of times you're going to have to remember that a tangent line or a line segment is making that right angle right there. So for me, it's helpful to redraw it over on the side as just the triangle because that kind of helps me put it in context. I have 12 for the radius, 16 for the other leg of the triangle on the tangent, and then I have this kind of like unlabeled piece. I know that this outside is x. Well, this distance from the edge to the center has to be the radius. It's the same distance as the radius is over here. The radius is the same all the way around the circle. So if I plug that in, what that's going to look like is 12 plus x becomes our hypotenuse. I do a little math here. This simplifies to 400 on the left. And because all of this is inside of parentheses, I can do the square root on both sides and just be left with 12 plus x on the right-hand side. Now, the square root of 400 happens to be a very nice number, 20, and that leaves us with just a little subtraction at the end. So, tangent lines are very helpful because they tend to form right triangles. Now, you can determine if it is a right triangle using the Pythagorean theorem, or you can use the Pythagorean theorem even if you have to add pieces together to make one of the sides of the triangle.